And I don't throw something on Wednesday or Thursday. So I'll try to get through all the topics soon. If you guys don't, you know, if there's a credit question, you can talk to me about it, or Kayla or Charlie can help. If you're interested in tackling the problem. So what I want to talk today is take what we've learned about hydrogen and move to other atoms. We're going to have to do that empirically in this class. We don't have tools. In fact, there are no tools in some sense to write down an equation like we did for hydrogen for the energy part. See this next module. We talk about systems that have multiple electrons. Right? Helium. So one atom down the periodic table from hydrogen, you have 2 electrons. And there's a new force that gets added to the Hamiltonian. You have 2 electrons. You have now an electron-electron repulsion. You have 2 electrons that are sharing the same region of space, if you will, with each other, and they repel each other. Okay, so there's an additional force that gets added to the Hamiltonian, the energy that is associated with this potential energy, this repulsive potential energy. By adding that additional term, you would effectively making it possible for you to solve the Hamiltonian exactly for the wave function. Right? Write down a formula and say the 1s orbital looks like this, and it's this energy. So you can get this formula here, like that's the energy. You can't do that for helium. We'll do a kind of a characteristic calculation of that probably next class. Right, to show you that you can't actually solve this problem. So what we have to do is what we've maybe learned as we've gone through this class is that we learn a very simple model like hydrogen or a spring. We can use that information to understand things that are more complicated. The framework, right? Hydrogen will be a framework for us understanding atoms that are more complicated. Right? And that'll be our goal going forward is using hydrogen as our, in some sense, our fundamental unit of chemistry. We know exactly how hydrogen works. The quantum mechanics is linear. Right? If we have a hydrogen-like electron, maybe a helium atom in some sense is the sum of 2 hydrogen-like electrons together. We'll use that concept of linearity where we take a simple problem to represent a more complex problem with a sum of solutions, multiple solutions representing one state of this complex problem, using multiple states of hydrogen. Hydrogen, helium 1s orbital in some sense is like a sum of hydrogen 1s orbitals. This idea of building things out of simpler things, building things up. That's the target that we want to do. Right? That's quantitatively, qualitatively. That's the way we want to approach chemistry. We understand this hydrogen atom very explicitly. To understand that, we can take our logic and extend it to more electrons that we say are like hydrogen. You can start to understand things about bigger atoms. So that's our goal today, is to more qualitatively understand atomic trends from the perspective of hydrogen. In some sense, we're going to derive a periodic table in our own way. So let's just recap where we were. The thing that we drove home about hydrogen, when we don't think about the spin of hydrogen, the electron, right? You just have an electron from a negatively charged particle moving around a positively charged particle. We solve our equation, we get these energy levels that are exactly defined. It says that they're proportional to this number n, the principal quantum number, which could be 1 or 2 or 3 or 4. Proportional to 1 over n squared, and the proportionality constant is this Rydberg constant, which is 110,000 wave numbers or something like that, right? So the equation, let's just go to the next page. Right, this leads to an energy level diagram that looks something like this. We represent it with negative energy, saying that 0 energy is the energy of removing the electron, the ionization limit. We have all these negatively charged, negative energy states, right, which means they're attractive. Negative energy means attractive. These negative energy states relative to the ionization limit. And they're all the same level, right? So the 1s orbital is by itself. And then the P's and the S's for n equals 2, or the S or the P's and the D's for n equals 3, they're all the same energy. It only depends on n. So what we would get are these series of lines, the Lyman and the Balmer and the Paschen series of lines that connect one of the lower levels to all of the infinity of the levels above. Look at those very carefully. Right, but this is the result of hydrogen not including the spin of the electron. Right? Spent second half of last class considering the fact that we have an electron that is orbiting the proton, but the electron also has spin, which is an orbit in some sense, angular momentum about the axis of the electron. So the electron itself is also spinning as it orbits the proton because of the spin. And so we have to consider the system. I'll come back to that in a second. We have to consider what happens when we include spin in our unit. When we include the effects of this angular momentum that the electron always has. And spectroscopically, we immediately see the problem. This is the Balmer line for 2 to 3. But we saw that it's not a singlet, like we expect. All the levels at 8 and 3 are the same energy, all the levels at 8 and 2 are the same energy. You have one line. But we see a doubling. Right? And I argued that the only way that this could work, the most consistent response, is that both the n equals 3 and the n equals 2 levels are doubled. That there's 2 states there instead of 1. Right? The splitting is very, very small. Right? This splitting right here is it's less than a wave number. About half a wave number splitting, very small. Center frequency of this line is like 16,000 wavelengths, right? So it's a tiny, tiny energy wave. Compared to this distance between these two levels, the 2, 3, and 2, 16,000 wave numbers, this splitting right here is about half a wave. Right? So it's a tiny, tiny energy shift. Very, very small, but it's spectroscopically observable, even in 1921. Right? So my opinion is that in spectroscopy, you have a spectrometer that can resolve a splitting, then that splitting is significant enough to analyze. If we forever always just saw these 2 lines blur together, who cares? Can't actually observe. I mean, it may be interesting that something's going on underneath the hood, that this splitting has always been there. But if you're an experimentalist, you only want to analyze what you observe, right? That's somewhat sophomoric. I mean, it's a little complicated. Sometimes we want to observe things that we don't see because we don't always trust our eyes. But even in 1920, you can resolve the splitting with very basic diffraction gradients. It's something that begs for you to analyze. Right? That this energy level structure that we've come up with, this 1 over n squared, is not 100% accurate. There's this finer structure. It's doubling of these states. And we rationalize the doubling of these states by introducing something called spin orbit coupling, where the spin of the electron is coupled to the angular momentum of the electron around the proton. So you have 2 forces, 2 angular forces acting, 2 torques acting on the electron, 1 orbital and 1 spin on its own axis. And there's 2 different ways to represent that. One is that the spin is the electron is spinning in the same direction as the angular momentum, right? So they're concerted and they're moving together, right? Which would lead to a state of higher angular momentum. It has L equals 1 and S equals 1/2. So the sum of those would be 3 halves. Or they could be working against each other, where the total angular momentum would be 1 minus 1/2. Have a total angular momentum of 1/2 versus 3 halves. These states have different angular momentum. And the idea is because they have different angular momenta, they have different energies. And so we did some vector work to show that the 2 possible states, if you will, for the p orbitals, is that there's a state 3 halves where the spin adds to the L equals 1, the 3 halves, and a state where they work against each other, where it's 1/2. 2 different J states, right? So each level, each p orbital, if you will, each p state in a hydrogen atom is doubled into these 2 J states, these 2 angular momentum states. They're, in some sense, the real states. They're not really SP states so much. They have p characteristic, really associated with states that have 3/2 and 1/2 angular momentum. All right, and we walk through the rules on how to calculate these. The idea is that we have this new quantum number for the total angular momentum J, which can take any value between the difference, the absolute value of the difference of the two angular momentum you're adding to the sum. All right, so it's very easy to do this calculation for hydrogen for the p orbital. Here, the minimum value L1 would be 1 for the p, L2 would be 1/2. 1 minus 1/2 is 1/2. That's the minimum value. And the max value would be 1 plus 1/2, 3/2. There's only two possible states, the 1/2 state and the 3/2 state. And what that means is therefore the hydrogen p orbitals, the p states, are doubled into two different states. They are split very, very slightly. The effect is very small. All right, and let's talk a little bit about that effect. This is the topic I forgot to discuss in the other section. Let's look at that splitting here. All right, so the 1s state has L equals 0 and spin 1/2. There's only one combination of 0 and 1/2, which is 1/2. 0 minus 1/2 absolute value is the same as 0 plus 1. So there's just one state for the 1s state. And the p orbital, the n equals 2 state, is split into two, 1/2 and 3/2. Right? And there are different energies, right? So this is from NIST. Right? These are reference values, right? And they're split very, very slightly. They're split by about a third of a wave number. This is about, the splitting's about 0.25 wave number, sorry, quarter of a wave number. Right, this is for the Lyman alpha line, right? So the line itself is 90, almost 90,000 wave numbers, right? It's 193 nanometers, a very, very high energy UV photon that takes an electron from 1s to 2p in hydrogen. And that state is the spin couples to the angular momentum just slightly enough to cause a splitting between in the p state by just a quarter of a wave number, right? That's a tiny fraction of the actual frequency. Right, so the spin effect is very small. So spin orbit is small for hydrogen. All right, but it's observable. Completely observable. In fact, there are even smaller splittings that appear with hydrogen, which we won't talk about in this class, where the electron couples not only to its spin, but the spin of the proton in the nucleus. That's what's called hyperfine splitting, where the electron couples to the spin of the nucleus. That effect is 1,000 times smaller than this. About 1,000 times smaller. And that also causes a splitting called a hyperfine splitting. So each of these levels are actually split again into much narrower lines, including this 1/2 line down here. This line actually doubles when you include the spin of the nucleus, and the spacing of that splitting in the 1s orbital due to the nuclear spin is tiny. It's about, the wavelength of that light is 21 centimeters, which is about 1.3 gigahertz. So this line actually splits again because of the nucleus, and the splitting, instead of 0.25 wave numbers, is closer to 2.5 times 10 to the minus 5 wave numbers. Tiny splitting, but it's observable in the microwave. Called the hydrogen recombination line. It's one of the brightest emitters. This 1310 megahertz hyperfine line of hydrogen. One of the brightest emitting radio lines in the universe, right? We studied that tiny little splitting transitions between the two levels of that tiny nuclear splitting of the 1s state using radio telescopes. And the whole spectrum, everything brightens up. Like anything that has hydrogen brightens up like bright white light. Like the whole galaxy glows in 1310. The sun glows in 1310. The sun glows so much, this tiny little frequency, the splitting between these levels so much that you can use a direct TV dish with some cheap electronics and actually monitor the sun's hydrogen with the cheap electronics. this little splitting here, the n equals 1 state. Right, so the idea is that as you start to include additional new sources, right, we include the spin of the electron, splits the p states. When we include the nuclear spin, it splits all of the states even more into smaller, tinier splittings. And that's one of the things that we see in chemistry all the time and spectroscopy all the time is that you have this general picture of these energy levels. But that picture always gets more complicated as you get better and better resolution. You look at smaller and smaller splittings, there are new effects that appear. And we can include the spin of the nucleus or the spin of the electron. If you're really, really careful, you can consider the interaction between the spin of the electron and the spin of the spin coupling. That's a tiny, tiny splitting. And people have studied that in hydrogen as well. So everything kind of talks to each other. We just have to make a choice on when to say, hey, we're okay with the analysis of the precision that we have. This is a good enough depiction of the atom for us to do our work. And so spin orbit is kind of the natural place for us to go. This is kind of the picture that we always see of atoms when we take spectra of them, right? Unless you're really trying hard. Okay, so let's talk a little bit about this split. All right, what causes these systems to split? Go ahead and copy this over. Hopefully it will copy. Yep. Okay. All right, so let's say there's some delta E between these two. Between the 3/2 and the 1/2 state. Where does that splitting come from? Now we can actually derive for hydrogen exactly the value of this split. We can write a formula down. Because again, we know hydrogen exactly. We know its wave functions. We calculate anything we want about hydrogen. We can write down exact values, and it'll teach us something about the general trends of this coupling, spin orbit coupling throughout the atoms. What you find is that through a bit of quantum mechanics, you find that delta E, or sorry, let's just say the energy of a state with quantum number L, spin S, and total angular momentum J is equal to 1/2 HC times this special constant, which I'll call A. Put a little tilde on it to specify that it's in wave numbers, times JJ plus 1 minus L plus 1 minus S plus 1. All right, so if we know the value of J, L, and S for a state, we can calculate the splitting. But we have this number A that we don't know, which is a constant. This is what's called the spin orbit coupling constant. And it's atom dependent. So each atom has its own coupling. Right? Certain atoms couple the spin in the orbit more effectively than others. And it's a function of J, L, and S, right? The value of the J, L, and S, which you can just write down. Right? So we'll do an example in a second. Right? Now, for hydrogen, for hydrogen-like atoms, and by hydrogen-like atoms, I mean ones with one unpaired electron. You can calculate A exactly. A is proportional to Z to the 4th. Z is the nuclear charge of the atom. So this is interesting, right? So as the atom gets bigger, the coupling between orbit and spin increases. Why would that be? Because we're not really talking about the nucleus. We're talking about the electron coupling to itself. Spin of the electron coupling with the orbit of it. Well, the bigger your charge in the nucleus is, nuclear charge, how many protons you have, the stronger the electrostatic potential is, right? You have more charges in the nucleus, you have an electron out here. That electron feels that nucleus more strongly if there's a lot of positive charges in it. If not. So if there's a stronger potential between a big nucleus and one Z with an electron, that electron will then therefore orbit much more rapidly. It actually orbits more close, right? It pulls the electron in closer to the proton, to the nucleus. Right? Nuclear charge is stronger, it's more attractive. Brings the electron in closer, which causes it to spin faster. Right? There's more centrifugal force, more angular momentum. Therefore, it kicks up the amount of angular momentum the system has. Therefore, the coupling gets larger, right? The angular momentum gets bigger. So big atoms have a lot of spin orbit coupling because those electrons are orbiting very, very rapidly. It's also proportional to this number mu naught. If you've done some of the homework, you've seen this number already, divided by 4 pi. This is what's called the magnetic constant. I'll copy this over and I'll narrate everything for you. G mu B. It's another set of constants times 1 over the value of n cubed. Okay, so this coupling gets smaller as n increases. That should make sense because as n increases, the electron is getting further and further away from the proton. Right? So longer orbit, bigger orbit. So therefore the angular momentum drops. It's not spinning nearly as quickly. Therefore, there's not as much orbital angular. So the spin doesn't couple to it as effectively. So it scales as n cubed, right? So as n increases, the coupling gets smaller because the angular momentum is getting further away. I want to mark these because they're important. E to the 4th n cubed. And for coupling reasons, or for unit reasons, there's a factor of Bohr radius squared cubed. And then there's a function of L plus 1/2. L plus 1. Okay, so the amount the spin couples to the angular momentum, the orbital angular momentum of the electron, depends on how many protons you have in the nucleus, how much electrostatic charge potential you have. It's a function of how close the electron is to the nucleus. It's also a function of the angular momentum. Right? Because if you have, remember, the spin contributes a fixed amount of angular momentum. That's 1/2. Doesn't change. It's always 1/2. So if you have L equals 1, and you add 1/2 to it, the new angular momentum is 3/2, right? It's 50% larger than it was before. So you've increased the angular momentum by 50% by coupling the spin to a p orbit. Now, what if you're in an F orbit? Well, there L is 3. So you have an angular momentum of 3, vector of length 3. You're adding to it a vector of length 1/2, which would be 7/2. That's not a 50% increase. That's a small increase, right? Going from 3 to 7/2 is a smaller change than going from 1 to 3/2. So by adding the spin to something in the F orbital or the D orbital or some of the high orbitals, it doesn't affect it as much because the angular momentum, orbital angular momentum, is so much larger than the spin. That's why it's in the denominator. Okay, so what this means is that this is saying is that large atoms with core electrons in large atoms have massive spin orbit coupling. Right. Now that extra credit problem on the homework discusses this. It looks at the halogens. So you can relate the halogens. I give you the spin orbit coupling for each of the halogens in the p state. Each of the halogens has a different n for experiments, different z. Think about that a little bit. There's some scaling involved. Give you a list of spin orbit coupling constants for different p states, different electrons, or different atoms. It should scale as z to the 4th divided by n cubed. So think about that a little bit for the extra credit if you're interested. All right, so let's just do a quick example. Go ahead and move this over. So for hydrogen, just as an example, for hydrogen, this all simplifies to 1.1608 times 10 to the minus 22 joules divided by n cubed L plus 1/2 L plus 1. Okay. Let me just say a couple things about the constants up here. Right. This is what's called the magnetic permittivity. Right. Remember that epsilon naught number? This is the magnetic equivalent. So the magnetic permittivity tells you how effective can you transmit magnetic forces across the vacuum. Remember epsilon naught, the electric permittivity of free space, which we see in the hydrogen energy. That's the electric version. That's how able you are to transmit electrical force or electrical energy or voltage across a gap in the vacuum. U naught is the equivalent for magnetism, so it's related. How easy it is for things to transmit magnetic forces. G here is what's called the G factor, and it's basically 2, right? It's just the number 2. And this is what's called the Bohr magneton, right? It's the magnetic dipole of hydrogen. Okay. So this tells you, so let's see, the coupling is dependent on how much can magnetic information transmit through the vacuum. That's important if you're thinking about spin. It's dependent on the strength of the magnetic dipole of the spin itself. And then also the electronic conditions of the electron. So we have some magnetic information, nuclear information about the magnetic properties of the spin, about the electronic properties of the spin. Red is magnetic. So again, spin is associated with magnetism. But this information tells you something about the coupling of the magnetism of the electron associated with spin and the electronic bond. Right? Which is spin orbit coupling. You have electronic orbital angular momentum. You have spin angular, which is the magnetic thing. It's coupling of those two. So for H, you have this value. The energy, what you can do is energy of the calculate of the L equals 0. Or sorry, L equals 1. S equals 1/2. J equals 3/2. And then subtract it from the energy for L equals 1, S equals 1/2, and J equals 1/2. Right, so this would be the splitting between the two P states. This is the P splitting. The 2P splitting. Of course, this is N equals 2. I'll write N equals 2 down here. And for the 2P. And this calculates to exactly 0.3659 wave numbers. Just by calculating everything out. And experimentally, and we'll just quickly calculate it. Go ahead and calculate it really quick. This score by 82258. Yeah, the experimental value is 0.3659 wave numbers. It's exact. All right, this is in some sense the real success of our hydrogen here, right? Here's a really, really tiny effect and height. We predict that there is an interaction between the spin and the orbital angular momentum of the electron that first appears in the 2p state. And we predict using quantum mechanics, we can actually derive this with a couple of integrals and wave functions. It's not too hard, but it's just not a problem we're going to work on. I get this formula out, and it predicts the exact value of hydrogen's spin orbit coupling. It's precise. Some insane number of digits. I'm in some sense truncated. It's better. This is the real success, right? Here I'm a priori about any assumptions whatsoever except for basic physics. I can predict a very, very tiny property of hydrogen to at least 4 significant digits. At least 4, if not more. Really, really small. Right? Really big success here. Okay. So let's extend this theory now to other atoms. Right? What can we learn about the spin orbit coupling hydrogen? How can we apply it to other atoms? What can we learn about? All right. Before we do that, I want to have a short couple-minute digression with a little bit of notation for us. All right, so we can talk about these things in a universal way. All right. So I'm going to give you just a small digression on some spectroscopic notation that we use in chemistry everywhere, including analytical chemistry, called atomic term symbols. All right, consider an electron, or consider an atom and some electron configuration. Let n be the highest value, the valence quantum number. Right? So e.g. n equals 1 for hydrogen or helium. And let L, big L, be the sum over all the electrons of their angular momenta. You're going to sum up over all the angular momentum of all the electrons in the valence. In valence, let's say that in valence. Oops, I had a computer freak out. Let S be the spins of all the electrons in valence. S. Okay. And let J be L plus S. We notate a state of this type, call it an atomic term symbol. Right, has this notation. First thing is the letter number n, specify the valence. And we have a superscript on the next label, which is 2, sorry, that's not a J, 2s plus 1, L, and superscript J. So by script, right? So let's do an example, right? L here we're going to write slightly differently. We're not going to write it in terms of numbers, but instead L can be again 0, 1, 2, 3, 4, 5, and instead what we call them are S, P, D, F, G, H, and so on. Okay, we use the orbital notation for L. Okay, and J is just a number, S2S plus 1 is a number, N is a number, and so on. So let's do a quick example just to give you some ideas. Right, so here's an example. Let's just do hydrogen. Let's do the first couple states of hydrogen. Right, so let's do the 1s state. Right, L here is 0, N is 1, S is 1/2, and therefore J is 1/2. So how would we write this? Well, remember we have it's N 2s plus 1 L J. So this state would first have a 1 on the outside because N is 1. 2s plus 1, 2 times 1/2, 1 plus 1. So we have a 2 subscript. L is 0, so we write S. And our J is 1/2. So this is the 2s 1/2 state. Right? This 2 right here we call a doublet. Right? Just for traditional sake, it's called a doublet. This is obviously not a doublet, it's a single line, right? But I'll show you an example where the doublet notation makes sense. All right, so we call this the 2s 1/2 state. If I go back to NIST, you'll see that it has a configuration, 1s electron. Its term is doublet S, just like we wrote with J 1/2. Right, so this notation is also used commonly. It's an IPAC notation, it's a NIST notation, it's completely standard. So this is how we often talk about atomic states. Specify the spin, what we call the spin multiplicity. I'll write that down in a second. Maybe the angular momentum of the electron of the state, total angular minimum of the state, and then the total orbital angular minimum of the state, and then the total angular state including the spin. All right, so every state is labeled with those 3 terms. And this number appears what we call the spin multiplicity. We're going to see why in just a second, why it's a doublet, why it's called a multiplicity. Right? It's not really clear in the 1s state. So let's move up to the next state. All right, let's look at the 2s state, right? N equals 2, L equals 0, S equals 1/2, and J equals 1. And so, again, same analysis, right? The only thing that's changed between the 2 S's is the N number, the principal number, right? So this is the 2s 1/2 state. Let's do the 2 P's now. N equals 2, L equals 0, L equals 1, S equals 1/2. But remember now, J can be 2 different numbers now, right? J can be the sum of L plus S, but it can also be the difference of L plus S. There's now 2 terms, 2 different states. J can be 3/2 or 1/2, either one. So the 2P has 2 states. One is the 2P 3/2, or the 2P 1/2 state. This is why we call them a doublet, right? This is a spin doublet. There are 2 different states due to the spin. Because of the spin addition, we get 2 different J's, which is common for a doublet. Doublet, typically, if you have a little bit of angular momentum in the system will split into 2 states. It's a doublet with the spin. Okay. These are, again, total common labels. If I specify this, I mean exactly the 3/2 state, or mean exactly the 1/2 state. Let's do something a little more complicated. I'm going to erase this multiplicity down below so I have it just a little more space. Let's go to the next page. Let's do helium. First, think about the 1s2 state, right? The ground state. What what would the term symbol for this be? Well, let's think about it. All right, we have two electrons now, right? So let's just think about them together separately. So we have two electrons, we'll call them N1 and N2, right? They're both N equals 1. The angular minimum of both is 0. The spin is 1/2 for both. But we have to account for a special fact about two electrons in the same orbital, right? Right now they're in the same orbital. Two electrons, right? We have to apply now Pauli exclusion. What does Pauli exclusion say? Pauli exclusion says that no two electrons may share the same state. So, and we implicitly know that, right? Because we have, right, in an orbital, 1s orbital, right, we're going to have a spin up and a spin down electron, right? One is minus 1/2 and one is plus 1/2 spin. So we have in our system now, even though the electrons are spin 1/2, their angular minimum have to be pointed in opposite directions. Have to be, by definition, right? There's no way to have two electrons otherwise. One has to be up, one has to be down. Right? So for a two electron system, we need to think about the spin projection on the z-axis. So we think about m sub s, and we'll say one is plus 1/2, which is spin up, and one is minus 1/2, spin down. Now let's calculate J. Right? J is going to be the sum over L plus sum, or we could say rather, yeah, that's well, actually what we should say is let's sum over, let's do the m sub j's instead, right? So let's double check, right? So m sub j, or sorry, m sub L for both of these is 0. Right? Because it's L equals 0, that's the only possible state. So instead of adding L and S, let's add by Z component, right? Which is kind of the way that we constructed the problem anyway. So what we can write now is a sum over m sub j states. We could say that m sub j, the total possible, is going to be the sum of m sub L plus the sum of m sub S. We have to consider that it can go from minus to positive. We have to do all the counting rules, but that's not so hard here. But this isn't so hard, right? We have 0 plus 0 for the L's, right? Because they're both S. And m sub S is 1/2 minus 1/2, right? Because they're different signs. This is S. And so this is equal to 0. All right, so the ground state of height of helium, S, the total spin is 0 because the one spin cancels out the other one. So this is a n equals 1. It's what's called a singlet. 2s is 0 here. Total spin is 0. It is an s orbital. And it has j equals 0. Right. So this is what we call a singlet state. Right? And a singlet state is just a fancy word. Well, it's not always the case, but a singlet state typically means that your electrons are paired. Your valence electrons are paired. Call it singlet. There's only one way to write it. Okay, spin up and spin down. No other way to construct an orbital that's a singlet, an orbital that's a singlet without carrying. One possible way to do it. That's why I call it singlet. All right, so interestingly, something that we can learn from this, systems, atoms and singlet states are non-magnetic. And atoms and doublet, triplet, etc. states etc., are magnetic. This is a consequence. So when you put a hydrogen atom in a magnetic field, it interacts with that magnetic field. The unpaired electron interacts. Right? This is the basis of, it's not really the basis of NMR, that's the proton. But there's another type of magnetic resonance called electron spin resonance, which is like NMR, but for the electron, it's like nucleus. And when you put the electron, what it says is when you put the hydrogen atom in a magnetic field, the electron, the spin of the electron couples to that magnetic field, and you can affect its motion. That's what magnetic resonance is. You can't do that with helium. You put a helium atom into there, at least as far as I can tell, put this singlet helium atom in, it does nothing. It has no interactions because the spins are paired. Anything where all the spins are paired is not magnetic. So helium doesn't interact at all. But you can't do spin resonance, can't do magnetic resonance, any sort of magnetic effect with spectroscopy on helium. It's not because of electrons. So because it's a singlet. So any singlet molecule is not going to be magnetic for any singlet atom. That's a really good way to tell whether something will be magnetic or not, by whether it's a singlet. Now let's do something that's slightly more complicated. Let's excite an electron in helium. Right? Things are getting much more interesting. And so let's look at excited helium now. Great, got plenty of time. All right, remember that in helium, so in multi-electron atoms, states of same N, but different L, have different energies due to electron repulsion, right? So that's why in helium, for instance, so in hydrogen, without spin, there's no electron repulsion because there's only one electron. You have N equals 1, N equals 2. There's 4 states there. 1, 2, 3, 4, 5, 6, 7, 8, 9. N equals 3. You have all the states are degenerate. No dependence on L, right? Energy is proportional to 1 over N squared, right? It's only dependent on that. But helium without spin, you guys know what you get here, right? You get an energy level that instead, or energy spectrum that looks like 1s, 2s, and 2p. And then it's 3D after that, I think, is the next one. And so on and so forth. Right? Because of electron repulsion, everything except for hydrogen, you get the classic example where you have the opt-out principle, right? Where you fill the electron 1s, 2s, 2p, 3d, and so on. The 3D, that's actually 3s, sorry. 3s is next. I should have done better. It's 3s, then 3d. Or I'll put one here. And then it's 3p after that. Right? Because the D's form first in the D block, right? Titanium and stuff like that. That's the next one. Right, so everything splits out, right? So there's L and independence for the energies. So energy is dependent on N and L, right? Some complicated formula, right? We don't have to worry about it. Depending on both. All right, so when we excite helium to its first excited state, we have in some sense 2 options, right? On hydrogen, when we excite from 1 to 2, it can go into a p orbital or an s orbital. They're not really s or p; they're J3 halves and 1 half. But here we have a very distinctive difference, right? There's a different absorption for the 2s and a different absorption to the 2p. Right? 2 different energies. So let's look at both cases. Right, both of these cases. Right, so let's look at so this would be, the first example would be the 1s1, 2s1 state. What are the ways that we can write this? Well, one of the ways that we can write this is the electrons can be opposite spins, but they can also be the same spin. There's two different possibilities, two different excited states to choose from. What are the term symbols? Well, it's not too hard to argue that this would give us a singlet, right? Because the spins cancel out. They're both L equals 0 states. You've just excited one to N equals 2, right? But it should be a triplet or a singlet state, right? So this one is just like the 1s. It's going to be the 2, 1, S, 0 state. Exactly the same analysis as before. But here we don't have a singlet anymore. Right? 2s plus 1 is 1/2 plus 1/2. That's s is 1. This is what's called a triplet state now. So this has a different spin. All right, so let's go ahead and do the analysis for this one. This one's a little more complicated. Complicated? No, I suppose it's not complicated. Let's go ahead and calculate it really quickly. Let me just get up here. So I just need to double check. So what would this state be? Well, first of all, it's N equals 2, right? 2s plus 1 is 3. So this is what's called a triplet state. L is still 0. They're in the S states. Right? And what's the total angular momentum? Well, there's no L because they're in S. So L is 0. Spin, you have a plus 1/2 and a plus 1/2, or they're both minus 1/2. And so J is going to be the absolute value of that sum or difference, that sum. And that's going to be 1. J equals 1. So this is what's called the triplet S1 state. So there are two different states and they have different energy. So I'll just write it here. This state is at 159,855 wave numbers. And this one is at 166,277 wave numbers. Notice that the triplet state is more stable than the singlet state. That should seem odd to you from a molecular point of view. Typically, we talk about molecules being stable when the spins are all paired. But in atoms, that's not always the case. In atoms, you're not worried about bond stability. Having triplets and bonds makes things reactive and make bonds break. But in an atom, you don't have that problem. You're not reacting. There's no bonds to worry about. Turns out that you actually, in small atoms, specific types of atoms, like helium, it actually prefers the triplet state. It wants the spins to be unpaired. It's actually more stable that way. I'll try to explain why that is by the end of class. Let's look at one more state. So that'd be the 1s1, the 2p1 state. Right? And we have the same option here. We have an electron here, and it can be in any one of the 3 orbitals, right? And then let me do it. Let me keep it consistent. So this would be one where they're both paired or they're flipped. So we have this singlet state, but there's also a triplet state. Bless you. I'm going to go ahead and copy this over to the next page. I need a little bit more room. So what would the energies of these be, or what would the calculations be? So let's look at this. Let's look at this first one here. All right, so this is the 2. This is a singlet state. The total angular momentum, orbital angular momentum of this system. Let me go ahead and sorry. 1s and 2p. The total angular momentum of the orbital angular momentum is 0 plus 1. 1p orbital, so this is a p state. Right. And what is the total angular momentum? J. Well, the spins are flipped, so the spin is 0, and there's only one unit of angular momentum, which is the p electron. So it's just one. J is one. So this is what's called the singlet P state. J equals one. Now, what about the other one? The other one's a little funky. So first of all, we can immediately write 2, 3, P. Right, because it's a triplet. Spins are unpaired. We have an L equals 1 electron. That's it for the total orbital angular amount. But what about J? J can take multiple values here. Right? Let's think about what the highest value of J can be. Well, J max is where we're going to take L, 1 plus L2, and add to it spin 1 plus spin 2. Right? And that's going to be equal to 0 plus 1 plus 1/2 plus 1/2, which is 2. So there's a J equals 2 state. Right? What other values can L take? Well, L can be 0 plus 1. And it can be 0 plus 1 minus 1/2 minus 1/2. That would be 0. Right? So there's an additional state, the 2, 3p 0 state. And then the final state would be 0. Let me think of how I calculate this. So that would be the 0 minus 1. No, sorry. How do we get that? And then, so that's the minimum state and the maximum state. And there's also going to be every value between them. This is J min. Right? And J will vary. J can be in between, can be any value between J min plus 1 to J max minus 1 to J max. Right, so it takes in every value, every integer value between J max and J min. And so there's also a J equals 1 state as well by construction. So an additional state where the angular minimum add to 1. This is why it's called a triplet. This is why we call this a triplet state, because there are 3 possible states. When you have 2 unpaired electrons and a unit of angular momentum, you get 3 states into triplet. Right? This is where these names come from. Doublets come from the p splitting that people observed in the 20s for hydrogen. And the concept of a spin triplet comes from the fact that you observe this in the p state of helium. Very classic. So quite interesting. Now, one of the really interesting things about atoms is that this has important consequences. And let me explain those important consequences. First of all, what I want to talk about now is, remember that we're talking about spectra, right? So energy levels, anytime we're talking about energy levels, we should be thinking about how can we explore them with spectroscopy. How can we explore these levels with spectroscopy? How do we manipulate atoms with light to move them from one energy to another? And atoms have a set of selection rules that give you the allowed transitions. Right? So the general selection rules for spin coupled atoms question is you go from one state of some characteristic to a state of another characteristic, which ones are allowed and which ones are forbidden? And the rules are quite simple. The hardest rule of them all, maybe not the hardest rule, actually this one gets broken sometimes, is that the spin cannot change. No spin flips. Right? So the consequence of this, there is no transition between the 1,1s0 state and the 2,3p states in helium. Does not allow. In fact, no state, no transition between states of different multiplicity are allowed. Okay. So in helium is very, very interesting. And you see this effect in a lot of different things. Hydrogen turned out to be the same. Hydrogen, molecule hydrogen, same properties. There's a triplet form of helium, the triplet P's with all sorts of different triplet states of helium, because there's 2 electrons that can either be paired or unpaired. So in helium, you either get singlets or triplets, the only possibilities you have. The singlet states are impossible, do not talk to the triplet states at all. If you excite a molecule into a triplet state, it can't relax to the singlet state without weird things happening, right? By light. So in terms of light, helium actually exists in 2 different forms. There's a singlet form of helium and a triplet form of helium. Again, they all have the same, one's magnetic and one's not. They have different chemical properties, different physical properties. You can't interconvert between them using light. There is a group of singlet heliums that exist on their own and a group of triplet heliums that exist on their own, and none shall the twain shall meet. There's 2 different forms of helium, triplet and singlet helium, right? So in terms of chemistry, of course, we don't really care. Helium is just a noble gas, but spectroscopically, it's very important. You have a process that creates helium. That turns out that process often, if you have something that generates helium, it's very rare, but you come up with a process where you can release helium. You will have mechanisms that create singlet helium, mechanisms that create triplet helium, but they won't create both of them at the same time because the delta S equals 0. So either you have a singlet state that forms a singlet helium, or you have a triplet state that forms triplet helium, and none shall the twain shall mix. Ever. Always separate. I'll show you a picture of this in a minute. The last one is that delta L has to be plus or minus 1. All right, so this means that S to S is forbidden. And that's true for all atoms. This is a hard rule. Very hard rule. And finally, delta J can be 0 or plus or minus 1, but J equals 0 to J equals 0 is forbidden. So these are the 3 selection rules. All right, these specify all the possible transitions between states of atoms. L has to change. J can either stay the same or change by 1, and spin cannot change. All right, everything else is totally free. One more set of rules I want to talk about. So now let me just show you one. Actually, let me show you a picture. And in the last 2 minutes, I just got a few rules to talk about. So let's look at that helium spectrum. I told you that they, in some sense, helium exists in 2 different independent forms, and neither shall they mix. And so here is an energy diagram of helium that splits the singlet states or the triplet states and shows you all the detected transitions, right, that are in units of volts. Or these aren't wavelengths, but regardless. Picture, right? And you see, so this is the 1s state, right? It's a singlet 1s state. And here's that triplet state. There's actually 3 of them. You can see there's 3 here. There's 0, 1, and 2. And as you can see, all the states are connected. They don't cross. There's no crossings. Right? There's no crossings because delta S is equal to 0. They can't cross. So you have 2 different manifolds of energy levels for helium that are, again, pretty close in energy, right? The singlet N equals 2 state is pretty close in energy to the singlet 3p state. This is the 1s0 state, right? They're pretty close in energy. But you can't connect them at all through with light. And you can excite the singlet manifold, and you'll never be over here. You'll always excite this. Meanwhile, you can construct triplet helium. You can make it, and it will always be in an N equals 2 state. It's impossible for it to ever cool down to N equals 1. So triplet helium is always excited. So this is the triplet ground state. It's always excited, right? So it takes energy to make triplet helium. Right, so when you go into the lab and you pull out the helium canister, there's no triplet helium in that. To be fair, the triplet helium is too high in energy. But you can certainly construct triplet helium if you heat it up or you apply some sort of energy to it, use a magnetic field, for instance. A couple different ways to do it. And that atom acts spectroscopically completely separately from the other atoms. They don't interact with each other at all. Completely separate, as if they're 2 different atoms. Right? And this is something you see in molecules, you see it in atoms, you see it everywhere. The idea that spins do not flip. Singlet states are separate from triplet states. Very rarely do they flip. There are very few exceptions to that rule. And the ones that are exceptions to that rule are extremely important. Extremely. In fact, a spin flip is one of the reasons why the photosystem in a photosynthesizing plant works. The electron transfer process that carries that energy for photosynthesis to make O2 relies on a spin flip in one of the zinc fingers in photosystem 1 that does a forbidden transition from a singlet to a triplet, or a triplet to a singlet, which allows you to flow energy through the membrane of the chloroplast on the transfer energy down to the electron transfer chain. Right, so spin flips do happen. They're very rare. They happen very slowly. But when they do, they're extremely important. Okay. Just for the last couple of minutes, I just want to summarize a few rules. All right, so these are general rules for atoms, for atomic states. All right, we have a special name for these called Hund's rules. And they specify something about the energetics of different atomic states. Right? What are more stable? Which ones are more stable than others? Right? So for a given electron configuration, state with the highest spin multiplicity is most stable. All right, so an example is carbon. Carbon. How do we fill carbon? Well, we fill the valence, we fill 1s, 2s. 2s gets filled. Right? And we know that the electrons add to the p orbitals like this, right? This is what happens experimentally. But there's another way to write it, right? There's lots of other ways to write this electron configuration. We could pair the electrons in the p orbital. Right? We can also pair the spins, but have them in separate orbitals, so they're half filled. Why is it that it's not these other two? Well, here, what is J max? Well, it's 1 plus 1 for the 2p electrons, plus 1/2 plus 1/2 for the spins. J is 3 here. Here, J max at most is 2. And it's a spin singlet. So S is 1 and S is 3 here. And then here we have J max is equal to 2. S is 1 as well. And so the most stable one is going to be the one with the biggest multiplicity, which is the triplet state. Right? This has the largest S and J. So stable, right? So this is how Hund's rules, number one, is how we fill electrons into orbitals, right? We don't pair them immediately. We add them one at a time, right? Because that maximizes the spin multiplicity to have them all unpaired and add one at a time. It also maximizes J. That explains that. The second rule is for a given multiplicity. A state with highest L is most stable. So a 1d2 state is more stable than a 1s0 state, for instance. Some way you can arrange the electrons so that it has lots of angular momentum, more stable. And then finally, for atoms with less than a half-filled valence, bless you.
Here.
The level with lowest J value is most stable. And then for atoms with more than a half-filled shell, highest J is most stable. So let me just prove that to you really quickly. Put it in class. Again, let's look at two states that are two atoms that are very similar in terms of their spectra, which is fluorine and hydrogen, because they both have one unpaired electron. Again, let's look at the stability of the p states in hydrogen. Right, and this is hydrogen. The most stable state is the 1/2 state, where the spin is acting against the electron's orbit. And let's look at fluorine now, which again has one unpaired electron. It has a p state as well. Very similar to p state. Not the best drawing of this, but or the best tabulation of this. This is in fluorine. Ignore these numbers. Ignore these numbers here. I'm just going to cross them out. This is in fluorine. Right, and you can see here the 3/2 state is at 0 wave numbers, and the 1/2 state is at 400 wave numbers. So 3/2 more stable. Now, why is that? 10-second explanation. atoms with empty valences have little EE repulsion. Right? There's very few electrons around in a valence, meaning they want to be close to nucleus. Right? They pull themselves in, right? So the last thing you want is to have a lot of angular momentum. That again has a lot of centrifugal force that pushes you away. And so if you don't have a lot of electrons between you and the nucleus, you're just going to come in, right? You want to come in as close as possible, which means you want to have as little centrifugal force as possible. Right? So that refers to 1/2, right? To low angular momentum states. Whereas full valence have a lot, meaning they want to be far away. Prefer long distance. Right, so they spin faster, right? The states that spin faster have more centrifugal force. Ones that are on average further away from the electrons in the core, the other perturbing electrons, and therefore is on average further away, it's more severe. Right? Electron repulsion determines this. Right, so EE repulsion, let's write that here, E repulsion controls the structure and energetics of atoms. Right? We'll see that a lot in this class as we move into molecules. When we start constructing molecules, we're going to have to consider the atomic orbitals. These effects to electron-electron repulsion are going to allow us to basically to construct electronegativity. We're going to find that this EE repulsion is the reason why we have electronegativity in bonds. And we'll see that in the next couple of days. All right, guys, have a good one.
That way I can actually go to PCAP lab tonight. And Abby won't yell at me if I get her sick.
She's always sick.
It happened twice last semester. Or because I'm always like, well, I don't want to make up the lab. I was like, you could just get the data from your group. And I'm like, I know, but I'm too nervous.